welcome to the second, I think it's the second of the RivEx Community Meeting. And we have to do this without our dear friend Cedric, because he cannot manage this time in California. That's what he said. So he gave his first presentation in November. So this is the second one of this quarterly community meeting. And I think there's a lineup also for me. I will talk in July, I think, and then Simon may also talk. So we have a lineup. If you go to the webpage, you see it. Actually quite a nice webpage. So, and today's topic is I read this out because it's quite a long title: Hydro Condition Topography and Hydrogeomorphology and Topo-bathymetry. Now I know what that is, but maybe some of you don't really know and are very excited to hear about it. But we have a great lineup of speakers, so I'm not going to introduce everybody. I would just like to say that each one could introduce themselves briefly before they start speaking. That would be easiest, because if I do it, I say we here for 1 hour, me just doing that. And I shut up. Simon is here also as a co-host with me. And Simon, if you think we could start the meeting, I would say we go ahead. And the first speaker is Dai Yamazaki. So he's going to talk about baseline topography and hydrography data for hydrodynamic modeling. And I hope it's going to be on a global scale, knowing Dai. So go ahead, Dai. I don't want to talk much more. And I won yourself 1 minute. So it's great.
Okay.
Thank you.
Yeah, thank you for introduction. So yeah, this is Dai Yamazaki from the University of Tokyo. And as a developer of the hydrodynamic model and also our global scale topography data. So I'm going to introduce the importance of baseline topography and hydrography data for hydrodynamic modeling. And I think all of you knows that water flows from higher place to lower place. But in the computer model, we have to represent topography as a data. And the accuracy of the flood simulation is highly depending on the quality of the topography data. So this is our nice example. So if the topography is not efficiently represented, the simulated flow dynamics is very different from reality. So high accuracy topography and hydrography dataset, they are key for a good river flood modeling. However, when we do our large-scale modeling, we rely on satellite topography data. But those satellite data, even fundamental elevation data, there are many errors existing. For example, what we need for flood modeling is the elevation of the ground surface. But what typically satellite capture is the elevation of the surface of the object. So difference of those two should be recognized as a bias due to forest or buildings. And satellite data also has many noise, and these are actually degrading the flood simulation quality a lot. So we have to handle these errors before using DEM in flood modeling. So what we are working is multi-component error removal from elevation data on the global scale. So I'd like to briefly explain my product, Merit DEM. So it's a multi-error removed improved terrain digital elevation model. So we start from the a bit classical SRTM elevation data, and we apply the 4-step filtering, which removes the stripe type noise and bias due to forest, and bias, absolute bias and the bias due to forest, and speckle noise. So by removing errors one by one, we can generate much smooth and higher accuracy elevation data. So anyway, this kind of pre-treatment of elevation data is mandatory for using space-bound DEM in flood modeling. And this is not the only one product. So recently, FabDem is developed by University of Bristol, and in their DEMs, they also removes urban canopy bias in addition to forest. And this is based on the Copernicus DEMs, so it's much higher resolution compared to previous product. And the machine learning based approach is used to remove both vegetation and urban canopy. So the new product captures the ground surface elevation more precisely. And yeah, compared to the other elevation data, we can see the ground surface is much better captured compared to the original one, and it shows a similar pattern compared to the LiDAR product, which is more precise. Anyway, so this kind of treatment is needed for flat modeling. And in addition to the elevation data, DEM, we need a hydrography data. So this is another important input for river flood modelings. So satellite elevation data, DEMs, are typically too coarse to resolve the river channels. So this is let's say this is elevation data, but we cannot see the river channel topography. So because of that, river location should be given by external water body map, like OpenStreetMap or other satellite-based water map. And by combining those two, we can add river topography to the elevation data. And this is named hydrography data in our community. So hydrography is primarily a raster-based river topography data, which is consistent to the original elevation data. And hydrography map typically contains multiple data layers, such as the flow direction and the flow accumulation. Those two are the most important ones. And optionally, we have a hydrologically adjusted DEMs and river width layers or river cross-section shape layers. Anyway, those is very important. And current standard product is, I think, our Merit Hydro dataset. So this is a hydrography data based on Merit DEMs and our latest geography dataset. So based on the Merit DM data, we combine many other water body layers, like Peckel's global water occurrence, GSWO, and OpenStreetMap. And how to say, by integrating elevation data with water body data and many other data sets like forest canopies or other how to say, ice and glacier layers, we generated a global hydrography map, primarily the flow directions rasters and the flow accumulation rasters. And we also calculate the hydrological adjusted DEMs and the river widths and the height above nearest drainage by using these dataset. And here is the result. So this is the main product. So this is how river networks is represented in 90-meter resolution raster data. So you can see the large rivers and smaller rivers in very detailed manner. And this one is the hydrological adjusted elevations. So in original elevation, sometimes downstream is higher than upstream, so it's not suitable for flat simulations. But in the adjusted product, we can clearly see the river lines. And in this adjusted DEM, it is the condition that the upstream is always higher than downstream, that is satisfied. So this is kind of a ready to be used elevation data for flat models. And also by combining flow directions and water body map, we calculated river widths and the height above nearest drainage. Also, this is a good indicator of the flood likelihood. Anyway, so those, how to say, primary flow direction data and additional supplementary layers. So these are I think, fundamental input for flat modeling. And having high quality merit hydrography data is very important. And this one summarizes the advancement of the hydrography data. So 10 years ago, we were using hydrosheds. That's how to say, previous standard. But this one is made by SRTM3. So that baseline elevation data contains lots of errors. But we updated the elevation data and we imported many water body layers. So the updated Merit Hydro, this has a higher consistency to national water layers, suggesting, anyway, that having a new latest input is very important to prepare the hydrography dataset. And so this is animation to show the importance of the baseline topography data for hydrodynamic simulations. So for both panels, I use same flood dynamics model, KEMA flood. So physics component are same, but the baseline topography data is old version on the left-hand side. But we use the latest merit DM and merit hydro in the right-hand side. And we can clearly see how the smooth and realistic expansion and shrinkage of the flood inundation. So anyway, this figure, this animation show that having a realistic topography data is very important for flood modeling. And I'd like to close my talk by defining some challenges. So even though I introduced latest topography and hydrography data, there are many uncertainties in those two datasets. So for elevations, we have to say accuracy, resolution, and the global coverage are still insufficient. And the LiDAR provide a high accuracy, but it only covers the limited part of the world. And the satellite DEMs cannot resolve key features for flood modeling, such as levee and embankment. And the current DEM failed to capture microscale topography, which is critical for flood inundation and wetland ecosystems. So those are still missing. And for hydrography, I think most big, largest limitation is development cost. So development and the continuous update of the hydrography data are highly labor intensive, and especially at the global scale. So update speed or update frequency is very small. So this is one limitations. And river channel cross sections data are largely missing. So this limits the physical realistics of the flow representations. And river network topology still contains errors, including insufficient verification and channel connectivity. So we are having some latest datasets these days, but these are not yet fully represented. So I'd like to say this is a challenges. So I'd like to finish my part here and maybe pass mic to Peirong. Thank you very much.
Thank you, Dai. That was great as always, and thanks for putting these challenges, because that leads a bit of a way into the discussion at the end. By the way, we changed the schedule slightly, that the discussion where all should participate is at the very end. So without further ado, let's keep your questions all towards the end, or put them in the chat. But we move on to Peirong Lin. It's going to talk about vector-based river hydrography. Thank you very much. Floor is yours.
Yeah, thank you. Can you see my screen well?
Yes, I can see it, but not with presentation mode. I see it as a PowerPoint.
How about now?
Let me give it a minute.
Does it work now?
I still see it as a normal PowerPoint with all the slides on the side, but
sorry.
You may see it as full. Yes, I know.
Let me do it again, maybe. Can you see my screen right now? Let me see. Can everybody see my screen well now?
Yes, now it's perfect.
Okay, all right. Yeah, thanks
great.
very much for the introduction, and thanks everyone for this opportunity to talk about our work on building vector-based river hydrography and building vector-based routing schemes, and some of the recent work to enhance the attribute to better characterize the riverine systems globally. And so this is work done by my lab members in collaboration with the great collaborators as listed here, and many others. Okay, so I hope I can use the next 10 minutes to briefly talk about the merit basins, which is built on top of Dai just mentioned, the merit and merit hydro product, and how we build the routing schemes on top of that, and also how to map different sources of hydrography data sets, and then to some of the recent work to enhance the attribute descriptions of the riverine system. And so why do we need vector-based hydrography datasets? Because vector hydrography actually better depicts the real world. They show realistic centerline locations and planform geometry. And actually, this data structure has the intrinsic flexibility to integrate with other irregular features such as dams, reservoirs, lakes, etc. And also, they have better alignments with remote sensing, so they can have better integration capability for data assimilation or integration and also vector-based schemes are having better computational efficiency. So they are becoming vital inputs to large-scale river models, such as the U.S. National Water Model. So previously, I've been working with the U.S. National Water Model for a few years, but it's difficult for us to scale it up to the global scale. But thanks to Dai, who has provided very important DEM dataset, and as well as Merit Hydro, the raster hydrography datasets, we created the Merit Basins dataset, which is a vectorized hydrography dataset using a channelization threshold of 25 square kilometers, and that delineates about 2.94 million river reaches across the whole globe. And for globally, we have discretized the river networks into segments of a medium length of 7 kilometers, and each flow line also comes with a local drainage contributing area with a medium area of 37 square kilometers. We've been building this data set also the top 2 levels data organizations following hydrosheds levels. For example, one represents Africa and following a clockwise rotation and all the way goes to Arctic and Greenland. And so in addition to these vector shape files we've been building, we also created basic attributes that are needed to create a global routing scheme on top of Merit Basins. And this includes the identification numbers of river reaches that is inherited from NHT Plus version 2. So that is also named COM-ID, and also come with length, sinuosity, slope, upstream drainage area, stream order. Those are attributes useful to calculate the routing parameters. And also, very importantly, we've created the river network topology on top of Merit Basins. So this kind of next down ID and max upstream drainage area, a max number of 4, also inherited from the U.S. National Water Model. And so this serves as the basic attributes that we provide with Merit Basins. And over the years, using these shape files and also the attributes we created, there are a number of global routing schemes established on top of Merit Basins. Those are including our 2019 work that couples VIC model with a rapid routing scheme established on Merit Basins, and that creates great naturalized river discharge product. And over the years, we have also had Yuan Yang and Ming Pan from UCSD further upgrading the model configurations to 3-hourly, and also most recently to update to replace the VIC component with the LSTM data-driven model. And also, this is Dongmei Feng's work, also established on Merit Basins, but on the hill slope routing model HRR. And that creates the radar and GDAR product, one representing Arctic version and another is a global version of the discharge, but then further assimilating river width. And then we have seen also a Mizu route established on Merit Basins, and also another rapid version established on Merit Basin to estimate global channel storage change. Okay, so now because we have created the Merit Basin vector hydrography datasets, and a number of global routing schemes have been established on top of that. And so our next question is, how can we map different sources of hydrography data sets together, because they have different advantages. For example, GRAL is enhanced with the Landsat river observations. And then we have also the very classic hydrosheds, that is the previous standards, but of course it also has the rich attributes that are very important to describe the riverine system, and also SWOD enhanced with SWOD, and also the most recent University of Oxford product, GREAT, that is also describing bifurcating channels. So over the years, we've been trying to making some attempts to link these data sets together and trying to enhance their descriptions. And one of the earlier efforts that we've been doing is relatively simple. That is basically trying to use a dense river network and then find the midpoint of each river ridge in the dense river network, and then find the nearest river ridge in the less dense river network. And then that creates a one-on-one mapping, but from the dense river network to the less dense river network. And that creates a mapping between GRAL and Merit Basins, and Merit Basins to Hydro Atlas. And we've been sharing some of the mapping tables and codes as well. And most recently, very good work from Cedric Davis' group, Jeffrey Wade. They have also created merit basins to sort mapping. That is a more complicated mapping between one-to-many translations. One river segments can be partially overlapped with, intersected with other segments. So all the intersecting IDs and weights can be documented, so the translation can be more efficient. So recently, we've been also developing a efficient Python mapping tool and using their weight tables and mapping tables provided. And so that can help us to transition between global river models created based on merit basins and the salt. And so this is just how this mapping looks like. And we believe that it's important to translate the prior knowledge to remote sensing data and also to use remote sensing data to create constraints to models. Okay, and so lastly, because now we have models and different hydrography data sets initially linked together, another very important question we can think about is how can we improve the attributes or the better describe the river and systems using the satellite observations, right? So previously we have to make these kind of simplified assumptions on the channels, but actually the channels are following the continuous shape parameters, for example, using the Dingman's R, or actually their spatial scaling is not a simple function with increasing with stream order or discharge, right? But we have to use satellite data to inform us how wrong we were in previous assumptions. Okay, so using this kind of mapping tools, we have preliminarily revisited the scaling relationship using river width. For example, we find out the previous power law scaling of the river width actually can only explain 30 to 40% of the variance in the width variability. But if we actually sample each one of the river channels with its attributes using a data-driven approach, that actually enhances the river width variability, explained variance in the river width variability. And we find out elevation, aridity, groundwater, soil composition, and some human factors also matter for describing the width variability across the whole global river network. And based on that, we can also create a data-driven prediction of the global bankful river width and also demonstrate machine learning as a feasible tool to estimate spatial variability of channel geometry parameters. And also now we have SWOT observations, because SWOT observations can actually give us simultaneous observations of the water surface elevation and width. So we are also trying to use SWOT observations to better constrain the heap symmetry curves that can give us better channel shapes. So recently we've been developing a SWOT method that is pre-processing of the SWOT node, river SP node product, and trying to improve its water surface elevation and width rank correlation. And then also to add some prior knowledge of a low control point and a high control point, and trying to estimate the whole curve fitting to estimate the heap symmetry curves. And then we also perturbed on certain parameters in these heap symmetry curves and trying to better quantify the uncertainty with this process. And by having this kind of fitted heap symmetry curves using SWOT and a prior knowledge, we can substitute the Manning's equations submerged area, and then based on these curves, and then we can evaluate whether that brings gains to the discharge product. And our preliminary results shows actually it performs better to some of the existing algorithms in terms of discharge because of the constrained channel shapes. And very recently, we've been also trying to add some other further pre-processing steps for the SWOT data sets by adding a width calibration module. And each one of these processing steps can help us better depict the channel shapes. And so that gives us some of the global patterns of SWOT observed channel side slope. And then, as you can see here, that shows us that some of the high slope areas are well aligned with our understanding of complex terrain and highly vegetated area. And some of the low side slope areas overlap with barren or downstream areas. And so that gives us some global patterns of channel shapes. And across the, in the next coming 1 or 2 years, we are expecting more and more this kind of data sets coming out of SWOT. And also, we are trying to better describe the riverine system by estimating the time varying confinements. For example, dams can attenuate flood peaks, and also levees can elevate water surface elevation and flood wave celerity. But previously, we do not have a reach-based estimation of this kind of river attributes. So we've been trying to, in the Pearl River Basin, conducted a case study trying to add this kind of time evolving attributes to better characterize the river system. So in summary, we've been creating a set of vector-based hydrography data sets on top of Dai's work, and also on some enhanced attributes. And we have been holding these data portals, for example, in Reach Hydro, National Tibetan Plateau Data Center, and also Zenodo data links. And also very special thanks goes to Mingpan and Yuanyang, who created very good interactive tools and maps to show how the hydrography data sets and the creating models on top of these data sets. And so the summary is that we've been creating merit basins as backbones for a number of global routing schemes already. But we realize there is also increasing need for interoperability of different hydrography data sets that are very important for us in the coming few years to map satellite observations with models, and also for us to create richer attributes for use to improve models. And so for that, I hope I can stop here, and we can leave some time for discussion on how can we better leverage different sources of data and how to better leverage remote sensing to improve models. And thanks very much.
Thank you. Thanks, Peirong. It's really great. I mean, there's a lot of information in there. I would have a lot of questions as well, but I really love the thing about how you explain the river width variability is something that's not easy. And the data-driven approach, I think, is quite timely as well with all this AI ML. So this is a good side of it, showing how you can really use these tools to explain a lot more that we couldn't do before. So anyway, there's a lot. And as I can tell, there's also a lot of this you put into open repositories and et cetera, and also tools for people to have a look that are not expert in this. So thanks a lot. Mm-hmm. I'm sure there's a lot of discussion things we can put to this.
Thank you.
So let's move on to the next one. Is a bit funny because I hope you guys have worked out who's going to talk, because between Paul, Steve, and Jeff. So University of Bristol, Fathom. I let you guys decide who's going to talk.
It's Steve.
Yeah, it's going to be me.
Okay, good. Thank you.
Let me share my screen. Oh, hold on. I might have to jump off because my Mac won't let me share my screen.
You're muted, I think.
No, I can't actually share my screen. I need to log off the call and come back on. So give me 2 seconds and I'll do it.
Yeah, we're good in time, don't worry.
While Steve is gone, Jeff and I should probably fill the gap.
Yes, if you could, that would be great. Yes, it may take him 1 or 2 minutes. Thanks, Paul.
Yeah, I mean, let's do the introduction stuff for the start. So I guess the work at Bristol has a slightly different focus, in that we want to build very detailed flood inundation models in order to create data sets that might be of use for the insurance industry or banks or finance. We know that flooding rather than routing is a very high resolution and local problem. And therefore, one of our key unknowns is river channel depth. So Steve's presentation is going to focus on the methods that initially Jeff developed for inverting to obtain river channel depths to plug into our global inundation models. And these run at 30-meter resolution over the entire planet and produce simulations of flood depths for those. So, Steve, I've just been doing a quick intro.
Yeah, thank you.
The application.
What is it with this computer
Thank
this
you,
morning?
Paul. So indeed, Paul already introduced the topic, which is this inverting bathymetry, which is very crucial for a lot of things, actually, to know how deep channels are. And of course, if you can do this globally, even better. So, yeah, Steve, unfortunately, I don't have your slides. Otherwise, I would say I can display.
Steve, do you want me to show the slides and you talk to them, or has he gone?
Yeah, I was just.
Right. Sorry about that.
Steve, if it doesn't work, I could share the slides. Oh, it's
I've got it. I've got it. Yeah. Sorry. Every time the computer updates, it asks me to redo all the sharing settings again. So sorry
Yeah,
about that.
you're there. I can
Yeah,
see
I'm
the
good.
full screen, so good. Thank you.
Okay, can you all see it? All right. Wonderful. So yeah, hello. Paul's given me a little bit of an introduction, but yeah, I am Stephen Shooter at Fathom, and today I'm going to be presenting our work that we've been doing on river bathymetry applications using SWOT and how it can be applied in a global flood model. And this is with Jeff and Paul at the University of Bristol, and a joint effort between us. So we've heard some really good stuff this morning from Dai and Peirong about why river channels are so important for flood inundation models. And we know that floodplain topography has advanced enormously over the last decade and a half, with Merit Hydro, FathomDem, FabDem, all coming in the last 10, 15 years. But we know that river channels are just as important in terms of parameterizing flood inundation models, but we don't really have many direct measurements of them. We know where they are roughly, but we don't know how deep they are and their channel shapes directly. But we do know we can infer those variables from water surface elevation and discharge if we know them using laws such as the gradually varied flow laws. So in terms of the current state of the art, what we typically do is have proxies for water surface elevation, river discharge, and geometry. So in terms of water surface elevations, to parameterize the channel depth, we typically take the dam height at the riverbank, which has about 1 meter accuracy, and then combine that with a 1 in 2 discharge from either global models or statistical analysis from gauging stations that we match similar catchments and port the characteristics over. And for that, we assume a rectangular cross-section, and then we combine all those variables to compute channel bed elevation using the GVF. And this is the best way we can do it globally at the moment, but has several caveats in the sense that the DEM is only accurate to about 1 meter. The 1 in 2 discharge, we may have no observations of discharge in a certain catchment. And we also assume a rectangular cross-section geometry, which we know, as we've just seen from Peirong, is becoming not applicable globally and is a crude assumption. But SWOT is a real revolution in what we're able to do in terms of monitoring water surfaces globally. It's the first time we've been able to see all major river surfaces every 200 meters, every 21 days. And this here is just an example from the River SP node version C data, which is all SWOT data mapped to the SWOT hydrography. And it gives us approximately 10 million locations and over this time period, about 700 million water surface elevations over this time. So that's like having a virtual gauging station almost everywhere on Earth for major rivers. And this data is at 0.1 meter accuracy. So we're looking at an order of magnitude increase than using DEM bank assumptions in order to parameterize water surface elevation. So if we go back to our original assumption, we can actually, our original sort of way of solving the bed, we can actually replace a lot of those assumptions with SWOT. So in terms of water surface elevation, instead of having just one assumption of bank fall height, we now have multi-temporal directly observed water surfaces from SWOT in the river channel itself. And then we can combine that with river discharge occurring at the same time as the overpass. So whether that's from observations such as GLOFASS grades, or from models such as GLOFASS or grades, or from observations such as gauging stations from the 10,000 that are approximately around the world. In our example here, we also assume a rectangular cross-section geometry, but that's something that we will expect to see over the next few years be rapidly changed in terms of our baseline assumption. And then we use the same assumptions and the same equations to calculate the bed that fits all those water surfaces. So in terms of our application, we take a river network. So typically we use SWORD, but we also use GRIT, which I'll come on to a bit later. And then we map discharge data, whether it be from observations for a model, to that river network, and then put that discharge into our steady state solver with the SWOT data. And effectively the optimizer optimizes the gradually vary flow equation so that we get the bed that best fits all of the individual SWOT overpasses. And then we use channel width from SWORD and other parameters such as Manning's N in order to solve this equation. And effectively, we're going from constraining this bed from one observation, that being a 1 in 2 discharge at a bank height, to being constrained by potentially hundreds of different elevation observations and discharge. So we should, in theory, get a much more realistic bed in order to put into our global flood models. And we ran this approach over the River Severn in the UK, and this is a study that's currently out in review and preprints in ESS Open Archive. And this is where we used SWOT version C data over the River Severn in the southwest of England, which is actually quite a small river. It's about 60 to 70 meters wide max, which is below what a SWOT was originally designed to see at 100 meters wide. And on the right here is all the dots here are the SWOT observations. The light green lines are the fitted gradually very flow water surfaces, and the black line here is the bed topography that we backed out of the GVF. And when we compare it to the observed bathymetry that we got from the Environment Agency in the lower sections of the River Severn and the upper section, we find that there's a pretty good fit. And it simulates the major features. And there are some spikes here in the observations, which are weir complexes, about 50 to 80 kilometers up the Severn's course, which our approach was never actually designed to model or see, but actually you can see it does start to resolve these features, but it's something that we should explicitly include in the future. And then when we plug that river bathymetry into a flood model for the River Severn, so this is the Upton upon Severn area, and we simulated it with discharge from the winter 2000 floods, we find that when we compare a model that's been built with a LiDAR topography floodplain and observed bathymetry, i.e. a sort of best-in-class engineering style model, compared to the same floodplain topography but with SWOT bathymetry, we find that the flood simulations are almost exactly the same between the two, and compare almost exactly the same with airborne SAR acquisitions at the same time. So what we can say from this sort of one simple test case scenario is that SWOT does have the potential, when using bathymetry conditioned by SWOT, to match a best-in-class field model. And we can sort of use it as a baseline for global applications based on the SWORD river network. But in terms of SWORD mostly represents single river channel networks with some bifurcations, but we know that 98% of floods actually occur with near a bifurcating channel. And this paper here from Telman et al. Went through the global flood database and found that 98% of floods are within a region of a bifurcation. So we need to really incorporate these geometry features in order to better simulate flood events in critical regions around the world. So this is work that Jeff's done at the University of Bristol. So effectively it's taken the approach that I described earlier and expanded it to these bifurcating channels. And on the right here is the GRIT topography that was described in previous talks. And what we do is take the SWOT River SP nodes and match it to GRWL, which is shared with, is the same baseline as GRIT, and do the condition solve with SWOT data on those river sections. And then on the tributaries and areas that are not covered by SWOT, we fall back to our 1 in 2 discharge assumption with fathomed end bank heights, and then match these two all up together in GRIT at the end. And what we get is a example here over the Mekong Delta, which on the left is a model conditioned by GRIT. Everything else is the same, but it has the GRIT with the bifurcations and GRIT without bifurcations on the right. And what you'll see is as this example evolves over time, we'll find that with the GRIT with bifurcations, the extent of flooding is much more widespread and flows much further downstream and breaks out a bank all the way down towards the coast. But we find that the depth is actually less, because of that extra spread, the depth is less concentrated, Whereas when we find with no bifurcations, most of the flooding occurs in the upper reaches of the delta system with a much deeper concentration in the upper reaches, but we don't get any sort of flooding towards the coastal area. So as you can see, just by including these bifurcations, you get a much different impression of what the flood looks like between the two, and just how important, especially in these delta regions where resilience is not always as high to flood events, is great to include these features. So to summarize, so SWOT is a transformation tool for river geometry understanding, and we've just really started to scratch the surface in terms of understanding the bed and still using assumptions such as cross-sectional channels. We know this is going to change a lot in the next few years. We have the potential to go from 1 meter to 0.1 meter accuracy based on looking at how we can condition water surface elevation alone in our bathymetry and resultant flood model. GRIT takes this knowledge and expands it further into bifurcating channels and simulating complex flood dynamics in delta regions. But we do know that bathymetry is dependent on discharge and the data sources used, so it'd be specific to the model and flood inundation model that's being used. And really, this is only sort of the beginning, because when SWOT was designed, it was designed to see rivers that are between 50 and 100 meters wide. But we know from recent meetings and results that it can actually go much smaller than this and see 20 to 30 meter wide rivers. So over the coming years, we'd expect to see SWOT to be able to apply to much smaller rivers and a much larger percentage of the total river network. So thank you very much.
Thanks a lot, Steve. Thanks. That's it's not a great presentation. There's so much, I think, that we have advanced, and I also have to be honest. I was expecting a lot this morning, but probably not that much of very useful new information that we could spend hours on discussing. So I don't know, Dai and Peirong have right now want to talk a little bit about the next steps. But I guess that after that, we're going to go straight into discussion. We lost about 5 minutes, but that's totally okay. I think we have 15 minutes to talk about the next steps and discussing it all. So,
Okay. Thank
take
you.
the floor.
Yeah, so before the open discussion, I'd like to maybe show something in mind as a next step, basically developed with Peirong. So we can think about to further improve the baseline topography hydrography data. And the first questions is obviously how can we integrate various river dataset. We have a raster hydrography like merit hydrosheds. And we have a vector river dataset like merit basins, sward, grid, and a national dataset like NHD+. So those three are developed by different community and used for different purposes. And they are similar, but actually it's difficult to integrate because sometimes we have a geolocation errors or sometimes river networks represented that slightly different. So how can we merge those two, or how can we put a bridge over multiple product that will be a next challenge. And the second one is how can we enrich the hydrography data with river-related informations. For example, we have lakes in addition to rivers, and we can think about how can we integrate river data and lake data. Those two are separately developed, but we have to think about how can we merge them. That's one thing. And the second important point is, as Steve introduced, we need a river bathymetry data, river cross-section data. And in addition to satellite estimated bathymetry, there are in-his surveys and sonar survey or nautical chart like this one. So we need to think about how can we, integrate these additional data to further enrich hydrography data. And the third challenge is, I think, very exciting. But we know, the current hydrography data is kind of static. But we should move from static to dynamic hydrography data by integrating the updated global elevation data or by integrating regional LiDAR-based elevation data. And also, we know the river channel migrate, and now we can observe the channel migration or morphology change from space. So, how can we use those latest elevation data or latest water body data to update the hydrography to the real status? So that I think will be our next big challenges. But yeah, this is a kind of open questions, so I'd like to ask your opinions. Oh, thank you for taking time.
Thank you, Larry. I have to say, I absolutely love to discuss number 2 and number 3 because I think they could be somehow related. Because number 2 for me is crucial. You know, like you say, you have all these river surveys that are done, yeah, in some countries more than in others. But how can we integrate nautical chart, everything that is out there for open? How can we integrate that into static hydrography, which would maybe be the first step in making it a bit more dynamic? Because when you have these ADPC measurements, you actually repeat those in most of the time. So that would already start giving you kind of a dynamic feel of it. But I think number 3 is crucial because everybody is expecting hydrography to be dynamic, but indeed in data sets, it's very often not. And just take the SRTM topography. I mean, it's a static topography. It's now very old, and even the Copernicus dam is getting old for massive flood events that change the morphology and the topography, especially in coastal areas. So I'd be very happy to discuss that. And I shut up now and leave the floor to other people as well. So we have about 10 minutes, a bit more than 10 minutes to discuss, and there's no real closing thing here. So after discussion, we could just leave. Thank you.
Thank you.
Somebody can start. Otherwise, I pick on maybe Paul. Why don't I pick on the most senior here?
Thanks. I guess the observation I'd make is just the rapidity with which LiDAR coverage is expanding globally. We've seen enormous advances in the area covered by LiDAR, particularly in the US as they finally sort of get on this on the LiDAR bandwagon a little bit, but also in other places as well. And I think we can expect that to move forward at pace. So the challenge, I think, as Dai correctly identifies, is then integrating all those new sources of regional LiDAR data with our satellite observations. And I think that's particularly important, and maybe underappreciated just how quickly that landscape is, no pun intended, but how quickly that area is changing. But I think I'd like to, I mean, Dai, Peirong, Steve, Jeff, and I talked a little bit in the run-up to the seminar, but I think I'd like to hear from people not involved in putting the presentations together what their take was. So particularly Simone, Hind, Payman, MJ, Fabrice, you know, what's your feeling here? What did we miss? What struck you as particularly important? I think I'd like to hear that.
Yeah, thank you, Paul. I may start with something that was mentioned by Peirong is interoperability, and I think it's very related to also the 3 next steps that Dai also mentioned, because integrating new data set or updating new data set to have a dynamical hydrography would be really easier if we have some kind of standard formats, and so that we can integrate more and more and make our different data sets that all of us develop more easily accessible to each other. So, to my opinion, interoperability is something very important if we want to remain able to integrate and ingest new data sets or updates of the existing ones. And with that also about the mapping between the different data sets and making them correspond, like what was mentioned with the Merit Basin and some gridded data sets like the old one, hydrosets, or the vector data set that is a SWOT, for instance. Maintaining a mapping is also very important between these different types of data sets. There are some methods to convert or to extract a gridded data set from a vector one or inversely, but I think we will continue developing these existing data sets and the different approaches. And for some applications, the gridded method is most suitable, and for some others, it's more reliable on vector one. So we need to keep this correspondence, this mapping between the different data sets. And to me, that's also falling into the interoperability of the data sets, actually.
It's a great point. It's crucial in all fields, right? This interoperability, and geospatial is one of those sciences that seems to have no limit on data sets, right? Every day, like petabytes of data just from satellites alone. And actually, I would love to see, just quickly, as an Earth observation person, I would love to see one of those commercial satellite providers getting some LiDAR missions up there. Because what ICEYE has done with SAR, I think somebody could do it with a LiDAR. Just miniaturize a LiDAR, put it up there on 60 satellites, or what do I know, 1,000 satellites now. And I just wait for that day where we would have a great constellation of LiDAR to measure topography. I mean, it's starting there. There are a few that are trying this, but it's easier said than done with LiDAR technology from space. But anyway, great contributions, Simon. I think if I can pick on some of the altimeter people that are there, the radar altimeter, maybe you have something to add. I know I see just a few names on my side on the Torian. I don't know if you want to talk, but you're also one of the future presenters, I guess, in this series. If you or one of your team wants to present, say something here, how altimeter data could be integrated more in these SWOT-derived databases to make it more dynamic, maybe. I don't know.
Well, this is of course a great point, but whether altimetry could actively be used because of the spatial temporal resolution of that would be a challenge. Of course, one could rely on geodetic missions like Cryosat, ICESat, and of course there were loads of good publication on that to bring ICESat into the whole hydrography stuff. More on lakes, less on rivers, of course. Of course, there's this data set from University of Munich where they have generated kind of river slope, global river slope using ICESat. I think this would be something to consider in general. But apart from that, relying on nadir radar altimetry might be a bit challenging for the whole context of hydrography. Of course, Fabrice can make a point. I mean, he has been doing this forever. But I think ICESat would be much more appealing in that context.
Yeah, you mean because of the footprint resolution?
Yeah, exactly.
Yeah.
Because of footprint and the challenges that it brings and the uncertainty of the whole thing.
Yeah, good point. Great. Thank you.
Yeah, mainly linked to the uncertainty, I believe, because it's still too high.
Okay.
It's not
I take this as from someone who knows that. So uncertainty is still too high. Is there any, I guess you're working towards reducing that, but it would still be, I guess.
Yes, we do work towards this.
Yes.
I don't know. RMSD of still like 20 to 30 centimeter. I don't know if it's enough. I don't know. We have to discuss with the people doing the hydrograph if it's. But I believe using the slope, maybe the slope from SWOT, which after a large filtering seems to be very useful, and especially because they provide like the temporal variability, maybe something like to include.
Yeah, great. Yeah, I think there should be more discussions among, different offline from these meetings on this community, because I think together we can really move ahead with these 3 points. Anyway, Peirong, I think you wanted to add something, right?
No, I think Hindi is going to talk about something.
Okay. Sorry, I didn't know who was trying to talk. Sorry.
Yeah, just all of you actually mentioned moving from a simple cross-sectional representation to one that's a little bit more detailed. And I'm wondering, in the context of global flood modeling, if that's actually crucial, or if it's more about the estimation of the area that's more important for those global models. I don't know if you have tried different shapes and if there is actually an improvement in the flood modeling.
So I guess either Jeff or I can. Let's let Jeff answer. He'll probably be more eloquent.
Yeah, Hind, it's a very good question. I mean, often, to be honest, we simplify to a rectangular channel to keep things simple because we're only interested in the out-of-bank portion of the flows. However, it can be difficult to calibrate, the friction parameters of a channel that's the wrong shape, for example. So it's kind of, I guess it depends on your application a little bit, but first order, we often simplify to a simple channel. However, there are downsides of that. And I think as the models improve and we get more and more kind of observation data to calibrate the models and things like this, then I think that assumption will start to become one of the issues that we would want to fix. So for me, it's kind of a moving target. Right now, we simplify to a rectangular channel just because it's one of the things to simplify and it makes life easier. But I don't think that will persist forever. I think eventually we'll end up with something more complicated. And the Dingman channel that Peirong presented is probably the next obvious step from that.
I agree, but I think to move to a more complex channel shape also involves having a better handle on the widths to start off with. There's no point having a complex channel shape if your widths have relatively high uncertainty, because that will dominate. And at the moment, swap widths are perhaps a bit too noisy for us to use and need a lot of smoothing. And growl and the like. Well, growl is conditioned by Landsat, 30-meter resolution. It doesn't see smaller rivers. So I think some of these things go hand in hand. If you want to have a more complex channel shape, you need a better handle on width, and you probably need a first order estimate of the friction coefficient as well, in some way. So we've got to solve some of these problems simultaneously.
Oh, I agree. And I'll say for maximum flood extent simulation, I actually feel the rectangular is fine. But for other applications like low flow estimate, and for example, more advanced ones like sediment dynamics, rectangular doesn't work, and we need more complex shape channels. So that is my current understanding.
Yeah, no, I completely agree, Dai. But to get there, we need not just shape, we need, width and friction tie into that as well.
Great. If I'm the bad one, I need to close this meeting. Any last 2 words of wisdom from anyone?
Can I just quickly add something here? I just want to say, according to my understanding of our this RivEx initiative, currently registered with GWEX, I think we are going to have this initiative actively going for the next 2 years, right? So, and also now we are seeing many new studies emerging from SWOT and other applications, right? So perhaps we need better mechanisms to share data more, how to say, actively, or just some better mechanism to share data. So just like Paul mentioned, many of the studies are going hand in hand, right? So we should have some better mechanisms to share data whenever they become available. So that may be helpful to others when they create global river models.
Yeah, true. I mean, just to say, I'm amazed how far we've come with the global hydrography data sets. I know it was all driven pretty much by SWOT mission, but if you go back 10, 15 years ago and see where we are today with these global data sets, they help a lot. And actually, one thing I would love to know is what other community uses them, except for those that create them, you know. But I think this is still a bit too far to now want to know who else is using it. But yeah, great. I mean, it's fantastic. I love the discussion. I love the presentations today. I wish we had more time, but we can always have more time in other community meetings like this one. So the next one, I think, is in April. So stay tuned. But yeah, thanks everybody very much. And thank you to the speakers. I don't know if anybody wants to add something. Simon, do you want to add some final words?
Well, simply a big thank for all our speakers this morning and the very interesting discussion that it just initiated.
Yes. Thanks to everybody. Thank you.
Thank you, Keith.
Thank you, everybody.
Pleasure to
Take
see
care,
you.
everyone.
Thank you.
Bye.
Thank you. Bye.
Bye.
Bye.